Hi, this is Kevin. Welcome to my lecture on Chapter 11 of the Zelle 3rd edition Python programming book. Chapter 11 is about data collections. As usual, I'm going to leave the objectives for you to read on your own. So we're going to begin with a use case for a data collection. And the data collections that we're going to be working with in Chapter 11 include lists, which we've already learned about. We learned a lot about them in Chapter 5, and we've been using them since. And dictionaries, which we've not worked with yet. And in this case, we're exploring a problem that is a great use case for a list. Okay. And so there are a lot of times when we need to calculate statistics on some data. Okay. And typical descriptive statistics might include the mean, the standard deviation, and the median. Okay? And up until now, when we've been processing data, we've done a lot of it with a file. Well, the thing about a file is that you can only look at one record at a time. Okay, and to calculate some parts of these descriptive statistics, in particular the standard deviation and the median, we really need to process through the data more than once. Now, we could read the file a couple of times, but what's a lot more useful is to, provided that the file is a reasonable size, read the file, create a list, and then process the list as many times as we like. And that's where we're going to be heading. Okay? So, the first thing we do is that we look back at some code that we wrote in Chapter 8, which was simple statistics. And as I remember, we were at computing the average, which would be the mean. Okay, so this is back in Chapter 8. The program from the author was called average4.py. My refactored version was called average4 refactored. Okay? Okay. Now, does that do everything that we'd like to do now? No, it doesn't, because it's only calculating the mean. And as I mentioned, we're going to want to calculate the standard deviation and the median. Okay? So suppose we want to take that program and we want to extend it. And we want to compute not only the mean, but the median and the standard deviation. So what's the median? Well, the median, as you probably remember from your studies in grade school or certainly high school, it's the middle value. So it's the data value that splits the data into equal size parts. So if the data were 2, 4, 6, 9, 13, the median value would be 6, because there are 2 below, 2 above. It splits it into equal size parts. One way to determine the mean is to store all the numbers, sort them, and identify the middle value. And that's the way that we're going to do it. It works really well with a list. The standard deviation is a little more mathematically oriented, but stick with me and I'll try to demystify it. So the standard deviation is the measure of how spread out the data is relative to the mean. If the data is tightly clustered around the mean, then the standard deviation is small. If the data is, and here at the iSchool we actually say if the data are more spread out, the standard deviation is larger. The standard deviation is a yardstick to measure or express how exceptional a value is. Okay? Especially if we find a value that's pretty far away from the mean, we can see how far away from the mean it is in relation to the standard deviation, and then we'll get a pretty clear idea of how exceptional that value is. So here's the equation for standard deviation, and I think the author really likes this because, again, he's a math guy. Okay, and what do we get from this? Well, this we have a square root symbol. Okay, so we're going to compute all these things under the square root symbol, and then we're going to take the square root. That's the last thing that we're going to do before we compute S, the standard deviation. And this Greek letter sigma here says we're going to sum a series of values, and it's going to be this x bar, which represents the mean, minus xi, which is the current observation, and we take that difference and we square it. Okay, this is referred to as the square of the deviations, and we divide that sum after we've summed up all the squares of the individual deviations from the mean. We divide that by n, which is the sample size, minus 1. Okay. Now, it's a lot easier to see this when we convert it into code than it is for a lot of people to read this mathematical typesetting. Here, the x with the bar is the mean. X with a subscript I represents the ith data value, and n is the number of data values. The expression x bar minus xi squared is the square of the deviation of an individual item from the mean. Okay. The numerator is the sum of these squared deviations across all data. Sounds like a for loop to me. Suppose our data were, as we say here at the iSchool, 2, 4, 6, 9, and 13. The mean is 6.8, and how would we do that? Well, we take the mean is 6.8, and we would subtract each observation, and we would square that deviation and sum them, and so we get 74.8. And so we have 74.8 over 5, which is n, 1, 2, 3, 4, 5 values minus 1. And then we take the square root of that and we wind up with 4.32. Okay. So the math works out. If you're doing it by hand, it's kind of tedious. So we're going to write a program to do it. As you can see, calculating this standard deviation not only requires the mean, which can't be calculated until all the data are entered, but also each individual data value. We need some way to remember these values as they are entered, hence the list. So, I told you before we thought this was a use case for lists. So we need a way to store and manipulate an entire collection of numbers. We can't just use a bunch of variables because we don't know how many numbers there will be. In any case, probably too many to use just regular old variables. What do we need? Some way of combining an entire collection of values into an object. Well, in this case, that sounds like a list. So Python lists are ordered sequences of items. For instance, a sequence of n numbers might be called capital S. Okay. And it has a small s, 0, 1, 2, 3, and these are like index values. So if it was n long, then the first one would be s index 0, and the last one would be s index n minus 1. Specific values in the sequence can be referenced using subscripts, which is kind of a mathematical term, and it's a term used in earlier computer languages. We use index as the term for what we need to use to point to just the item that we want. By using numbers as subscripts, mathematicians can succinctly summarize computation over items in a sequence using subscript variables. So subscripts is the mathematical name. This notation here is the mathematical notation for how to sum that series of values. If this were a math course, that would be important, but it's not. It's a programming course. So how do we turn all this into programming? So suppose this sequence is stored in a variable s. We could write a loop to calculate the sum of the items in the sequence like this. Okay, so we'd set some variable to 0. Sum turns out to be not a good Python variable name because there's a sum function, and you do well to not choose variable names that shadow the names of built-in functions. So you probably don't want to use sum. You probably use total. So then you'd say for I in range n, sum gets assigned the value sum plus s sub I. So this is a tragedy of Python variable names, but it's very appealing to the author, who is a math guy, and we'll be straightening this out soon enough. Almost all computer languages have some sequence structure like this, sometimes called an array. So in computer science, when we talk about these kind of structures, these ordered collections, a lot of times we use the term array. In Python, they're called lists. A list array is a sequence of items where the entire sequence is referenced by a single name, single variable name, and individual items can be selected by indexing. We put the index value in square brackets. In other programming languages, arrays are generally a fixed size, meaning that when you create the array, you have to specify how many items it can hold. And this has been a problem for a long time. So the mothers and fathers of Python, when they invented lists, they just solved that for us. So that's one advantage lists in Python have over arrays in most other um, computer programming languages. Arrays are generally almost also homogeneous in these other languages. So they can only hold a single data type. So you have an array of int or an array of strings or an array of floats. Now this isn't a restriction on lists in Python. So Python lists are dynamic. They can grow and shrink on a demand. So we don't have a problem with size, which makes them very convenient. They're also heterogeneous. A single list that can hold uh, arbitrary data types. Now, having said that, if you're going to make a collection of something, it needs some theme, right? So usually the theme is these are a bunch of, kind of observation in data series. Well, they're all going to be the same type, right? Uh, when would you have a list where there are different types? Maybe this is a list of data that the user entered into a web form. Okay, well, there might be different data types there. Okay. Python lists are mutable sequences of arbitrary objects. One thing that we've learned about lists already is that they're mutable, which means that we can change the items on the list. So we can add to them, we can delete them, we can change their order by sorting. Um, there's just all kinds of things that we can do. And we've already talked about some of the list operations in previous chapters, but they include concatenation. So you can use the plus operator in order to concatenate two lists and build a new one. Uh, you can use repetition, so um, you can have the list uh, an asterisk and then a repetition factor or expression, um, which will throw off a new list that's a repetition of the original list. This turns out to be really helpful when you want to set all the entries in a list to 0. So you can create a list with 1 0 in it, and then you can use the asterisk to repeat that to create a list that says has 50 zeros or 1,000 zeros. You can use indexing expressions. You can use len to calculate the length. You can use slicing syntax to get a sublist. You can iterate over it, okay? Um, uh, you know, Using the for in construct. And you can ask if some item is in the list using the in operator. They're calling this the membership operator. And it returns a Boolean. Except for the membership check, we've used all these operations before on strings. The membership operation can be used to see if certain value appears anywhere in the sequence. So I guess here they're working at the console in the REPL. So I guess this is LST for list. Somebody give me an I here. And we use the list initializer and give it the values 1, 2, 3, 4. And then we type in the expression 3 in list, and we get back the result true because 3 is in the list. So the summing example from earlier can be written like this. again, I wouldn't use the variable name sum, but let's assume that we can, and we're not worried about that. So we set sum equal to 0, and then we say for x and s, horrible variable names, sum gets assigned sum plus x. Unlike strings, lists are mutable, okay? So if we have a list with 1, 2, 3, 4, and we ask what's in list 3, we'll get 4. We ask to set the 3rd item of list to hello, and now it says 1, 2, 3, hello. So you can't do that with strings because strings are immutable objects, but lists are mutable, and they're also heterogeneous, so you can do this. Now, what your rationale for it is an open question. We just wanted to show you what could be done. A list of identical items can be created by using a repetition operator. This command produces a list containing 50 zeros. So let's say that we were trying to use the list to represent the okay, so let's say that we had some kind of an accounting scheme for our company, which was a U.S. Company, and we had 50 states. And we knew, according to our codes, which number each of the states was, and we wanted to set up accumulators for each of the states. Well, we might initialize this list of accumulators by creating a list with a single item 0 in it and multiplying times 50, and now all the time the list zeros has 50 0 items in it. Lists are often built up one piece at a time using the method append. So here's a case where we create the empty list called nums, and then we prompt the user to enter a number. We convert it to a float, and we assign that to the value to the variable x, and we say while x is greater than or equal to 0. So I guess the value is going to be the sentinel value. So if it's 0 or less, we're going to stop. So if we haven't reached the sentinel value, we're going to say nums append x. Okay. And again, x is a float. And then, of course, we did this up top. This was a kind of a priming read. And then we have a while, which is looking for sentinel value. And then in the while loop, we do our work. And then we read again at the bottom of the body of the loop. Here's some list operations. So we've already talked about append. It's going to add this new element on the end of the list. Sort is going to sort the list. Okay. If this is a type that already has a built-in ordering, like ints and floats and strings have a built-in ordering, it'll sort on that order. And we're going to learn some more about that in a little bit. Let's say that we want to get the list in the other order. Well, we can just call reverse on it. Okay. What if we want to find the index of the first occurrence of some value, well, we can just say the index of value and we'll get the index value back. What if we want to insert a value? Well, we can say insert IX, where we're going to insert item X and index I. What if we want to get a count of the items? We want to get we want to know how many times a particular value occurs in the list. Like if there were strings and they were colors and we wanted a count of red. So we could say count red in parens, and it would count the number of times red occurred. What if we wanted to delete the first red in the list? Well, if we said remove, and then we gave the string red, it would delete the first one. And then we've got pop. We pass it a parameter I. It deletes the ith element of the list and returns its value. Okay, so why would you use a pop and not just, read the value using an index expression? Well, the idea here is you want to consume it. So not only do you want to get the value, you want to remove it from the list at the same time. If you're considering this some kind of a stack or some kind of a queue of things that are waiting, well, you pop it when you want to use it, and of course you want to eliminate it from the list when you access it. So, oh geez, here's a bunch of examples of how things work. So we have a list that ends with the value 9. If we append a 2, now it ends with the value 2. If we sort it and we look at it, and now it's in ascending order because these are all ints. If we reverse it, it's now in descending order. Okay. And then if we ask for the index of 4, it's going to be 0, 1, 2. You got a 2 back. If we say that we want to insert for hello, it's going to go to 0, 1, 2, 3, 4. So that 2 is going to go away. And the hello, I'm sorry, it's not going to go away. It's going to go in between the 3 and the 2 because we're inserting. If we ask for a count of 1, okay, we have 2 1s, so we get a 2 back. If we say we want to remove 1, well, we remove the first 1, so there's still 1 1 left. If we say that we want to pop 3, we go to 0, 1, 2, 3, and we pop it. So we get back the value 3. And then when we look at the list again, that value 3 is not there because we have consumed it when we did the pop. Most of the methods don't return a value. They change the contents of the list in some way. And I just want to contrast this with the methods that we learned for string, which even though the methods for string, like we're calling upper and lower and capitalize and title and those things, they appear to change the string. They don't change the string because strings are immutable. Instead, the expression throws off a new string value. So the code might look like strings are changing, but they don't because they're immutable objects. Well, lists are mutable objects, so these things appear to be changing, and they are changing. Lists that can grow by appending new items and shrink when those items are deleted. Individual items or entire slices can be removed from the list using the DEL, or I call it DEL. It's short for delete operator. So let's look at this. We've got my list has got 1, 2, 3, 4 items. So we say we want to del my list 1, so 0, 1, the 26 should go away. And if down at the REPL we type my list again, we can see the 26 has gone away. And then we can say, we can use the slice. We can say del my list 1, 3. Okay, so 1's the first one we want, 3's the first one we don't want. So we wanted to do 1 and 2. So we're getting rid of not 0, but 1 and 2. And then when we look at it again, there it is. The 0th one is the only one that's left. Del isn't a method. How do we know that? It doesn't have parentheses. So it's a built-in operation that can be used on list items. Okay, so let's talk about some basic list principles. A list is a sequence of items stored as a single object. Items in a list may be accessed by indexing, and sublists can be accessed by slicing. Lists are mutable. Individual items or entire slices may be replaced through assignment statements. Lists support a number of convenient and frequently used methods. Lists will grow and shrink as needed. Now, I think we mentioned, quite a few slides ago that the equivalent data structure and a lot of other programming languages is not so flexible. They don't grow or shrink as you need them to. The mothers and fathers of Python thought that having to worry about how long this sequence was a headache, and that's something that a programmer should have to worry about. So when they defined how a list was going to work, they made it very convenient for us. It makes me glad I'm a Python programmer. Now, we promised a whole bunch of slides ago that if we wanted to take our statistics program and have it calculate not only the mean but the standard deviation and the median, that the way to do that was to use a data structure that would allow us to keep all the values in the memory at the same time, and that is a list. So one way we can solve our statistics problem is to store the data in a list. We could then write a series of functions that take a list of numbers and calculates the mean, the standard deviation, and the median. Let's rewrite our earlier program to use lists to find the mean. Okay, so here's what I'm going to do. There's a program that comes with this chapter, and it's called stats. Okay, and I have an unrefactored version of this, and you can see it's got methods like get numbers, mean, stdidev, which is I guess it means the standard deviation, median, and main. Okay, now I have a refactored version of this I'm eventually going to explain to you that solves the typical problems that we get with the code that comes with the book. But I really like the conversation on the slides, so as I go through the conversation, I'm gonna use the code as it comes with the textbook, and then at the very end I'm going to show you how to refactor it to make it, kind of live up to the standards that I'm expecting in my course. Okay? So let's write a function called getNumbers that gets numbers from the user. We'll implement the Sentinel loop to get the numbers. And initially, an empty list is used as an accumulator to collect the numbers. The list is returned once all the values have been entered. So here's the code for get numbers. So you can see we begin, he decides that the variable is going to be nums, and he's going to set it to the empty list. And then he's going to do a priming read, okay, in which he saves the string that the user types, which might be the empty string if they just press enter to quit. He saves that in a variable called extra. That's the priming read. You'll see at the bottom of the loop on the while, as is typical, at the bottom of the body of the loop, we do the read again. The test for the while loop is extra not equal to the empty string. So we're looking for that sentinel value. Okay. We take this extra, which probably means x as string, and we convert it with a float and store that into x. We use append to append the float value onto the back of the list, and then of course we try to read again. Okay, so this is a function. Okay, it takes no parameters in, and it returns nums, which is a list of floats, which is going to be just as long as the number of values that we got from the users. Using this code, we can get a list of numbers from the users with a single line of code, which is to say, in our main function, we can just call get numbers, and we can assign the list that we get back to any variable name. I just want to point out that data is a horrid variable name. Everything's data. This is it. This is about data, okay? We would have done just as well to call this stuff, all right? Probably, again, I'm going to make my points about the refactoring at the end, so in the meantime, I need to behave. Now we need a function that will calculate the mean. So the input is going to be a list of numbers. That's the parameter we're passing in. The output is going to be the mean of the input list. That's probably going to be a float because the list that we're passing in, they're all floats. So let's look at this. At def mean, okay, we're passing in nums, okay. We're going to do some accumulation, right? So we set this accumulator for the sum to 0, and then we say for num in nums, then we're going to accumulate num, okay? And then we're going to return the sum divided by the length, okay? Now I'm just going to point out here, and we'll fix it when we do the refactoring, this can potentially divide by 0, okay? We have let the user decide how many values that they're going to give us, and because we're using a sentinel loop, and if they signal right out of the blocks that they are not going to have any input, now this is going to divide by 0. So when we refactor this, the code is going to be more robust than you currently see. The next function to tackle is the standard deviation. In order to determine that, we need to know the mean, right? So if you remember, the formula for the standard deviation is that you calculate the difference between the mean in each of the values that you have, and then you square that deviation, okay? So should we recalculate the mean inside of the function that calculates the standard deviation, or should it be passed as a parameter? I think the good practice is what the author does here. If this was a really long list, it would be wasteful to recalculate it. So what we're going to do is we're going to call the method, the function that we just had. We're going to call that to calculate the mean. We're going to call that from main, for instance. And then we're going to hang on to the value, and that's going to be one of the values that we pass into the next function that we're going to write. And this is a typical thing that we do. Could the standard deviation function recalculate it? Yeah, but it's wasted effort. So we're going to pass it in. Which is what slide number 33 says. I forgot there was a slide that said that. My apologies. Okay, so here's our function. And we're passing in, so the function is called stddev. And we're passing in nums, which is a list of the number values, and x bar, which is a mathematician's technical name for the mean. And let's say we have a variable name that's not properly formed that means, I think, the sum of the deviation squared is 0, and now we're going to go through and we're going to accumulate them. So for num and nums, first of all, we calculate the difference between the mean and num. We make that dev, I guess that's the deviation. And the sum of dev squared is equal to what it was equal to previously plus dev times dev. Now, if this is a way to square the deviation, we're already using square root from the math package. So when you see my refactoring of this, I figure, well, let's use the PAL function from math, which does exponentiation. So I've refactored this. I'll show you the details in a bit. So the summation from the formula is accomplished with a loop and an accumulator. Sum dev squ stores a running sum of the squares of the deviations. It does. And that's what we return a formula that calculates the standard deviation. We don't have a formula to calculate the median. Now, I just want to point out, this is true for the mean and the standard deviation as well. This isn't to say that Python hasn't got code to do all three of these things that we're doing here. So there is a package called statistics, which we could have imported and we could have used on our list, and then we could have called called a function from that package to calculate the mean, called a function to calculate the standard deviation, and a function to calculate the median. Okay, now those are part of a package That's part of formal Python. But when we say we don't have a formula to calculate the median, um, we mean we haven't articulated in our conversation here in the slides, we haven't articulated a formula for how to do it by hand because we're showing you how to do it by hand because we want to show you the value of using a list as a data structure when you're doing this kind of work. Okay? So first, we need to arrange the numbers in ascending order because we have to find the middle value. Second, the middle value in the list is the median. If the list has an even length, the median is the average of the two middle values. Oh, that makes sense. Okay. All right. So here's the pseudocode. Sort the numbers into ascending order. If the size of the data is odd, the median is going to equal the middle value because if it's odd, there is a middle value. Else, the median is going to be equal to the average of the two middle values. Okay, because if it's even, there's going to be two values that represent the middle. There's not just a single value. Okay, and then we're going to return the median. Okay, I think that's great pseudocode. I really like that. So let's look at how this translates into Python. So he calls the function that calculates the median, he calls it median, and he passes it the list of a data called, he's calling it nums. Okay, the first thing he does is to sort it. Okay, these are floats. They're going to sort into ascending order, lowest first. So now he wants to calculate the size of nums, so he calls len, okay? And he says that the mid position, that's what he means by mid pos, that's, again, a not properly formed Python variable name, is the size integer divide by 2, okay? And then he says, if the size modulo 2 is equal to 0, if there's no remainder when we divide by 2, that means we have two positions, okay? I'm sorry, we have two middle values, okay? So here's what we do. We say the median is equal to nums, and we use the index middle position plus nums middle position minus 1. Okay, so we add those two values together and we divide by 2. So we average them. Else, well then when we only have a single middle value, so we retrieve that using middle position, and then the answer is in median, so we return the answer. So that's pretty easy when you think of it. So now we need to code a main, okay? And we've kind of said what this is all the way along. He's typically, been printing some kind of a description of what the program does. One nice thing about that is you can see that the program is active and you know that you ran the right one. So then he calls get numbers, gets the list back, calls that the variable name data. He passes the list data to the function mean and gets back x bar. That's the mean. Then he calls standard deviation, stddev as I call it, and passes in the data list and the mean, which he's been calling x bar. And then finally, he calls median and passes in the data list, and he gets back a median value, and then he prints out the mean, the standard deviation, and the median. Okay, so this is, I think, a well-structured program. It goes about it in the right way. One thing that it does that I like in particular is it remembers that we don't want to recalculate the mean. This is really a wasteful thing to do. And of course, if we're running this program on our own personal computer, what do we care if we just use a couple of cycles? But let's say we're doing some kind of a data science thing on a shared computing environment, and maybe we're paying by uh, maybe there's a meter running. I mean, maybe it's Microsoft or Amazon is going to send our employer a bill, or maybe we're in some kind of shared computing service, and as soon as we use up all the capacity, the university or our employer is going to have to go a bunch, is going to have to buy a bunch more capacity. So we really don't want to be wasteful, right? So this, realizing that passing in the mean instead of recalculating it, I think that was a real good touch. And just the structure of this is very clear and sweet. Okay. Now, and then he decides that he wants to make this a module that he could import, and then he could call some of these functions. So that's the reason at the end he's got the more formal if dunder name equal dunder main call main. Now, I think that this is probably a weird idea. As I mentioned, there is a package that comes included with Python called statistics that has a perfectly good implementation of mean, standard deviation, and median. And it would be better practice as a working programmer to use those instead of coding these yourself or importing something that you created yourself. So this is he's dreaming here. Okay, he would have done fine just to call main, but let's humor him. Okay, so that's all the commentary on that program. Um, so I just want to show you how this works, right? So the program that again comes with the pack with the chapter. It's called stats .py, and it's all right here. Okay, and it's got a lot of warts. Okay, but if we run stats, okay, it says enter a number. I've got a series here. So here's what I'm going to enter. My first one's going to be 25. My second one is going to be 11. My next one is going to be a negative 44.4. The next one's going to be a 99. The next one's going to be a 1. The next one's going to be a 0. And then I'm done, so I just want to hit enter. And it says that the median is 6. Let's see what we got. So the mean is 15.2 and then a repeating 6. The standard deviation is 47.16, which is pretty high. And the median is 6. Well, that makes sense. Okay, now I didn't enter a 6. So you can see we've got 1, 2, 3, 4, 5, 6 values. So the median was 11 minus 1, that has a difference, and that's a difference of 10, and half of that is 5 added to 1 is going to give us a 6. So I've had to compute the average of the two middle values. Okay? All right, that works fine. Now, this program has a couple of problems. Okay? So what happens if we don't enter any values at all? Boom, float division by 0. Well, that's not good. Okay, and then let's run it again. What happens if we enter just a single value, 999? And boom, float division by 0. So this code is not robust, okay? And in the author's defense, you can only teach so many things at the same time. Okay, and what we were trying to teach was what's the use case for less that relates to computing statistics? And there's a whole bunch of things that you need to process more than one time. And this is the classic example that we use. Okay, now I'm going to show you my refactored version of this. So this is stats refactored. Now I've done a couple of things. One, I've done the usual, it has a doc string now, okay. It has an import. We were always importing square root, but now we're using PAL to do the squaring when we do it. It has a bigger main, and it's at the top of the program. In most normal programs, it's good practice to put your main at the top. The names of the functions are pretty much the same, but now they're Pythonic. They're regular snake case names: get underscore numbers, get entry from user, calculate mean. One kind of interesting thing is that I know there are a lot of built-in functions that say, well, there's one in the statistics package that calculates the mean, and it has a name mean. But for you and I, if we're going to write a function, it ought to have a name that hints at what it does, and it should typically have some kind of verb noun phrase. So don't call your functions mean. That sounds like a piece of data, right? Call it calculate mean. That's a piece of action. Okay, so the same thing for standard deviation. Calculate standard deviation. Calculate median. Okay, so pretty straightforward stuff there. Let's look at, did we change a lot of things in there? I just cleaned up the variable name. Nums. We can use the keyboard. Just call it numbers. Instead of sum, I made this total. I think it says sum in the book, and I think the program that came with the book, the program, they had actually changed it to total. You don't want to use sum as a variable name because it's got the same name as one of the built-in functions. When we calculate the standard deviation, first of all, when we're doing this accumulation, I use the plus equal instead of having used the name 2 times. this gives you the latitude to have a fairly long name, like sum of deviations squared. Okay? If you use the plus equal, you don't have to write it again. And then I think it's a little bit clearer that we want to raise it to the power of 2. We're already using the math package, so go ahead and call Powell and pass it the value and 2. He has a lot of these oh, it's not what I wanted to show you. Yeah, so those are just kind of dry cleaning that I did. In the main, okay, we don't want to calculate the standard deviation and the median, or really the mean, if we've got fewer than 2 values. Okay, because we're going to get divided by 0. Okay, so what we want to do is we just want to check. We get the count of the values that we have, which is the length of the list values. And if the count is greater than or equal to 2, well, then we do the calculating and we print the answers. I have upgraded the prints to use the more contemporary F strings over the call to the format method of the string class. And then if we don't have at least 2 values, then we want to print a warning, and we probably want to tell them how many values they entered. Okay, so if we go and run this, okay, let's see what happens if we don't give it any entry. Well, it gives us the warning. We entered 0 values. Okay, and let's run it again, and let's give it just one value, 9999999. Okay, and then enter, and it gives us the warning that we entered only 1 values. Now, could we have improved this to say you entered 1 value? Yeah, we could have. I just didn't have the energy. All right, and then if we go to calculate a real problem, I'll do the same one I did before. I start with the 25, 11, negative 44.4, 99, 1, 0, enter, and we get the same answers. All right, so not a whole lot of extra effort to refactor this. I guess the first thing that I did was to refactor it. The restructuring, to check the count, it's not technically refactoring because we changed the functionality. So that one part is really an enhancement, but all the rest is just refactoring the code to make it more Pythonic and the typical things that we refactor for. We want to make it easier to read, easier to test, easier to maintain. All right, so that's that code. Let's go on to the next part. Okay. So another use case that we have for lists in programs is this. We have some data records, okay? And these are data records that have more than 1 value on each of the lines, okay? And in the example that we're going to use here, each of the records represents a student in a university and their grading data. Okay, it's enough to calculate their GPA, their grade point average. Okay, and we want to do things like we want to be able to sort the records into a particular order. Okay, and there's an approach for this where we create a custom Python class that serves the function of being a data holder. It holds like one line of data from the input file. And we create a list of instances of that custom class. And then we can sort that into whatever order we wish. Okay. And then we can process it and or report on it. So that's what we do here. And here come the details. So all the list examples we've looked at so far have involved simple data types like numbers and strings. We can also use lists to store more complex data types, like our student information from Chapter 10. So we don't cover Chapter 10 in my course. In fact, the chapter that we use from for how to build a custom Python classes from the Severance book. But what I've done, and you'll see it in a minute, is I've taken the author's example from Chapter 10 and I've kind of cleaned it up to current standards, and I've used it in this Chapter 11. So in Chapter 10, they had a grade processing program that read through a file of student grade information and then printed out information about the student with the highest GPA. A common operation on data like this is to sort it, perhaps alphabetically, by credit hours, or even by GPA. And these programs, which we're learning to do here in Chapter 11, pretty typically what you do is you read the data file, you create a list of objects using the custom Python class, and then you sort that list, and then you run a report. And more typically, you'd like to see things in several sort orders. And so you do sort, report, sort, report, sort, report. Okay? So that's the use case that we're enabling with the approach that we're taking here. So he says, let's write a program that sorts students according to GPA using our student class from the last chapter. And I'll show you that in a minute. But here's the pseudocode. Get the name of the input file from the user. Read the student information into a list. Sort the list by GPA. Get the name of the output file from the user. We're actually going to write a sorted file. So this isn't the case where we're going to write a report, where we're actually going to sort the file. We're going to read the file in, sort it, write the file out. Write the student information from the list into a file. Let's begin with the file processing. The following code reads through the data file and creates a list of students. So the first thing he has here is he's got code for read students. Okay, and okay, so and again, this has got the dry cleaning problems that read students is not a proper snake case Python function name, but let's be tolerant. Okay. So in read students, we pass in a file name. Okay. And then we use it to open the file. And then we create an empty list called students. And then we say for line and in file, we call a function called, uh, uh, I'm sorry, on students we call append. That's how we add a new item. But what's the item? Well, we take this line from the input file and we pass it to a function called make student, which is a helper function that makes a new student object from the line from the input file. And so we go around and we read all the lines in the file, and for each one we create a new student object and we append it to the list, and then we close it, and then we return this list called students. Okay. Okay, so this would be a good time for us to look at this student class. Okay. And the student class is in a file that was in chapter 10, and he repeats it in chapter 11. It's called GPA.py. And he has a student class. Okay. And then he has a helper function called make students. Okay. And in the helper function, you pass it a line from an input file, a student record, as it were, and it builds you a new student object. That's how that works. Okay, now what about the rest of this thing? Well, the author is very fond of having your cake and eat it too. So in this one Python file, he's doing three things. He's defining a custom class that holds student data. Okay, that's a great idea. He's creating a helper function that, kind of helps you create those, because it can turn a line from the input file into a new student object. I could see why you would put the two of these in here. But then he's got some code hanging around from his chapter 10 where he reads all the student things and he finds the student with the highest GPA. It's kind of a find highest. And why you would want to put that in some kind of a library module is beyond my wildest imagination. Okay, and so if you go to my refactored version, you'll find out that we're using some different syntax to create the student class. This is what we're going to learn in my class when we get to Severance chapter 14. We're using a new capability that came out in Python 3.7 called data classes, and it creates a much easier way to create a data holder class, which is really one of the simplest use cases for custom Python classes. And so what I do is here in chapter 11, I give you the code for these data holder classes. You don't have to be able to write one. You don't have to be able to design one. You just have to be able to use one. And then when we get to Severance chapter 14, well, then you have to be able to design and create one. So all you have to know here is that this this class, a student object, has three fields: name, which is a string, hours, which is a float, and quality points, which is a float. And when you want to compute the GPA, you take these quality points and you divide them by hours, and you get the GPA. And then what I did is there's one method in the class called calculate GPA. His was just called GPA, so it was hard to tell the difference between this method and GPA is a more proper kind of a field name, not a method name. So calculate GPA just returns the quality points divided by the hours, which is the GPA. All right, so this is a much cleaner version of the class using capabilities that came along in Python 3.7. You won't be expected to create one of these in Chapter 11, just to use one. And then I refactored make student to have a proper name that's snake case and doc string. And I just kind of I used the new versions of the field names and the new versions of all the stuff to clean it up. And then I've got some code in the main here, but what this really is unit testing code. And does everybody put their unit testing code for a custom class in the main of the same module? No, they don't. Most software developers in the field use one of the unit testing frameworks, like there's one called Unit Test, which I think is the older one. And that's not something that we cover in my course. So I created a little bit of a homegrown version of it. And starting soon, we use this in order to do some unit testing. But all the code in the module has to do with the student class and the helper function, and there's no kind of crazy other program, kind of hanging off the bottom of it. Okay, and then I've got this GPA refactored. That's a GPA in the GPA refactored. Now, he has us working on, if you look at the code that we're looking at in the slides, this is a code for a program that he's included with the chapter called GPA sort. Okay, and let's make that bigger. GPA sort again has the regular kinds of problems that the programs that come with the book have, in that they don't have conforming function names and all that kind of stuff. So I've refactored that, but generally this logic works fine. So what I'm going to do is I'm going to go back to, well, I'm just going to show you the read students, right? So if we look at my refactored one, okay, what did I do in the read students? Well, I passed in the file name, I opened the file, I created a list of students that was empty, and then I said for line and file, and students, that's a list, append. Then we called the helper method make student, and we passed it the line. So what did we get back? We got back a new student object, which got appended, and we did an in-file close, and we did a return students. Okay, so this refactored version does about the same thing. Okay, it's just, well, just maybe dry cleaned would be the way to look at it. Okay, so he says here, we're using the make student, that's a helper function from the GPA module. So we'll need to remember to import it and the student class. Okay, and of course, how do we do that? Well, from GPA refactored import student, make student. Okay, so not too hard to do. Let's write a function to write the list of students back to a file. That's a kind of the corollary to read students is write students. And this is a really sweet design. I really like this. Each line should contain 3 pieces of information separated by tabs: name, credit hours, and quality points. Okay. Now, and that's what he does. So, I'm sorry. Where are we? Yep, right here. So, we're passing in the file name that's coming from the main. We've got the list called students. We open the out file. For S in students, we're going to do print. So we have a string that we're printing, and then we have file equal out file. Now I've changed this around a bit. His way that he accesses the field on the class is very much, it's not even old-fashioned. It's the way they do it in Java and not really the way they real Python people do it. Okay, so if you look at our version of this, it's more simple. Okay, so if we come down to write students, we're passing in the list and the file name. We open the out file. We use a better name here. We say for student and students. We want to print, we can use an F string. They're a lot easier to read than that version of formatting that he had been using. And in the version of the class that I have, we do what most Python people do. We just access the field. So if you want to access the name field on a student object, you just use the variable name that points to the student object. In this case, it is student.name. And then we have a tab, student.hours, and then a tab, student.qualitypoints. That's it. And then we have the file equals out file. And then when we're done with writing all of them, we have the out file close. Okay, so this is cleaner than what came with the book and more Pythonic, right? These calls to these getters, which you have here, that's the reason why we're not covering chapter 10. Again, that's the way people do it in Java, but it's not the way people do it in Python. Using the functions read students and write students, we can convert our data file list of students and then write them back to a file. All we need to do now is sort the records by GPA. That makes a lot of sense. In the statistics program, we use the sort method to sort a list of numbers. How does Python sort lists of objects? Well, to make sorting work with these custom objects, we need to tell sort how the objects should be compared. So we have to offer them, we have to offer the sort a way to get key values from each of the objects. And we can supply a function to produce the key for an object. Okay. Now this is a whole new approach. Um, um, so we'll look at the exact code, and then I'll make a comment or two. So to sort by GPA, we need a function that takes a student as a parameter and returns the student's GPA. So here's what we can do. We can create a function called use. Uh, he doesn't really do this in the end. He says you could create a function called use uh, GPA, and then we could say return a student call GPA. And then on the sort, the way that you tell the sort how to get a key is you use the keyword parameter key, and then the value, what's the name of the function to call. There are no parens at the end. We're not calling the function. We're we're passing it, so sort can call the function every time it needs to get a sort key from a student instance. Um, Again, we didn't put the parens after it because, again, we're not calling use GPA. Uh, Sort will call it. And in Python, functions are what we call first-class objects, and you can pass them as parameters. But when you do, they don't have the open parentheses at the end. They just have the name of the function. So actually, it's possible for us to not have to create a function for this because we already have a function that returns the GPA for a student. Now, in his version of the code that came from chapter 10, he just called the function GPA. And here you can see why that was a poor design choice, because that looks like the name of a field. Okay, it happens to be the name of a method. Now, if you look what I've done on my clean version, okay, let me get this. Sorry. Here it is. It's coming over now. Okay. We're calling, so here's what we're saying. It's the same thing, but the name of the method now, my method that calculates the GPA looks like a method name. It's called calculate GPA. We still don't put parens after it because we're not calling it, we're passing it to sort. Okay, so if you look in my GPA refactored, what's the method called? Well, it's called, is that GPA refactored? Oh, it's called calculate GPA, right? So then we have we calculate the GPA, quality points divided by hours, and then we return the GPA. Okay, so just a little bit of following good practice and how you name things leads to code like this, which when you write this, when you say that the key is the calculate GPA on student, it's pretty clear that we're talking about a method, you can tell from the name. So this approach is called inversion of control, which is a situation where the control during the sort is kept by sort, okay? And if we want to influence it, um, uh, we can influence it by passing it a little bit of code that helps to influence it. Calculate GPA. That's the code that will retrieve the sort key value. Okay, so we do get some control over the sort, um, but um, uh, they call us, the sort is going to call our code when it's ready for it. So some people in the industry refer to this inversion of control where you pass a function such that the code that's really in control can call it. They call it the Hollywood principle. And it has to do with the old line that a Hollywood agent would tell a new actor. The new actor would say, "Oh, I'll call you next week." And the Hollywood agent would say, "Don't call us, we'll call you." Okay. Who's really in control? Well, it's the Hollywood agent, not the fledgling actor. So what's really in control here? Well, it's the sort method, and we can offer a piece of code to be called to have some influence over the sorting. Okay, but the main control is going to be by sort. Okay, so that's how we do the sorting. Okay, we've come to the end of what it's turned out to be part one of the lecture. I didn't really think that this was going to be long enough to have a part one and a part two, but it's turned out that way. So I'm going to take a break, and I'd like you to do the same. And when we come back, we're going to finish off the rest of the lecture. And so please take a pause here, and we'll be right back. Okay, we're back. And as I mentioned just a little while ago, we're going to skip ahead. In my class, we don't cover parts 11.4, 11.5, and 11.6 from chapter 11. Because they cover features that we're not particularly interested in. So that corresponds to slides 51 through 105. So we're just going to very quickly jump ahead. And go to 106. Okay, so here we are. So, we mentioned at the beginning that this chapter was about collections, and the only collection we've talked about so far is the list. So we're also covering the dictionary. So the dictionary is a non-sequential collection. And it's probably after the list, it's probably the next most widely used collection data type. Dictionaries are not as common in other languages as lists, which in other languages are called arrays. But most modern programming languages, certainly Java has an equivalent that's used fairly frequently. So it's not like they don't, it's not like this kind of collection is unique to Python. So lists, as we know, allow us to store and retrieve items from sequential collections. So they're sequential, they have an order. when we want to access an item, we look it up by index, its position in the collection. What if we wanted to look students up by student ID number? In programming, this is called a key value pair. So the key value pair is the student ID is the key, and then the values associated with the student. In the example that we're using in this chapter, it would be the credit hours and the quality points. Those are the value. So we access the value, the student information associated with a particular key, student ID, key value pair. So there are lots of examples, potential use cases, names and phone numbers, usernames and passwords, state names and the name of the capital city. A collection that allows us to look up information associated with arbitrary keys is called a mapping. So mapping is a general computer science term. Our dictionary is an example of a mapping. Python dictionaries are mappings. Other languages call them hashes or associative arrays. Okay? So they do occur in other languages. Dictionaries can be created in Python by listing key value pairs inside of curly braces. Keys and values are joined by a colon and are separated with commas. Okay, so you can see a couple of things here. So this structure that we see that begins with a curly brace and ends with the opposite curly brace, this is a dictionary initializer, okay? And we are creating 3 dictionary entries. One that has the key Guido and the value superprogrammer. The second has the key Turing and the value genius. And the third has the key Bill and the value monopoly. Okay, and we've placed a reference to this dictionary in the variable password, spelled password, again, probably to save space on the slide. We're using indexing notation to do lookups. So if we were to type in at the REPL password Guido, we would get, that's the key, so then we would get back the value, super programmer. So in this case, the value objects are strings. So the variable with the name of the dictionary with an index of the key value returns the object with the associated key. It returns the value. Dictionaries are mutable objects. So if we wanted to change the value for the entry with the key Bill so that the value was blue screen, we could. And then if we typed in password, we would see all of the contents of the dictionary, and we would see that the value associated with the key Bill is now blue screen. Did you notice that the dictionary printed out in a different order than the order in which we created? Well, I hadn't really paid attention to it, but you could see we've got Guido, then Bill, then Turing. But when we created it, we had Guido, then Turing, then Bill. Okay, so what's the explanation for this? Well, mappings as a general computer science concept are inherently unordered. Okay, so Python dictionaries are an instance of mapping, so they are unordered as well. Internally, Python stores dictionaries in a way that makes key lookup very efficient. When a dictionary is printed out, the order of keys will look essentially random. So the order in which these entries are going to come out is not defined. If you want to keep a collection in a certain order, you need a sequence, not a mapping. So again, here we're starting to differentiate the use cases for lists as compared to dictionaries. Keys can be any immutable type. Well, let's think about that. What immutable types do we know? We just saw that you can use strings. Okay. You can also use ints. You can use floats. You could use booleans. Of course, you'd only have two different values there, not too helpful. Okay. Values can be any type, including programmer defined types. So values can be instances of a custom class. Oh, okay. And so values can be mutable or immutable. Like lists, Python dictionaries support a number of handy built-in operations. A common method for building dictionaries is to start with an empty collection and add the key value pairs one at a time. Okay, so this is how we do this. So we use this empty initializer with the curly braces. So this says, I want an empty dictionary and I want to associate it with the variable password. And then we could read the passwords off of a file. So we say for line and open passwords .r. So here we're opening a file and we're reading it with ever really getting access to the file object. We're just immediately using it as the subject of a for in. Okay, so we'll get each line, so we split each line and we split it into user and pass. I think we mean like username and password. And we populate the dictionary by, on the left side, we refer to the dictionary with an index of this username value, and then we assign it the password value. Okay, I guess we should say the username key and the password value because it's a key value pair. So what are the operations that we can do on dictionaries? We can use in to check if a key is in the dictionary. We can call keys to get a sequence of keys. This is a trick that we'll use and we'll see if we want to retrieve things in key order. Well, then we can call keys to get a sequence of keys. Even though it's a sequence, it's not a list, so we have to wrap that in a call to list. Now we have a list of keys. Then we can sort that list of keys in any order, and we can use the keys to access the values. We can do a call to values to get a sequence of values. Again, it's not a list, so if you want a list, you have to enclose it in a call to list. We can have a call to items. This returns a sequence of tuples, each one being a key value pair. Okay. Again, it's a sequence, it's not a list. So if you want to process it as a list, you have to enclose that in a call to list. You can use the del operator to delete a specified entry. You can call clear on the dictionary to delete all entries. Um, you can check if uh, oh, you can actually loop over the keys. So you can say for var in dict, okay? So you can visit each of the entries, not particularly in any order. If you want to do this in, say, the keys are strings and you want to do them in alphabetical order, you have to do a call to keys. You have to wrap that in a call to list, and then you have to do a for in on that list. And a really popular method of the dictionary is the get. It allows you to retrieve a value, okay? And one of the nice things is that you can provide a default value that you'll get back if your key is not in the dictionary. And we'll see that used in another couple of slides. So, if we call password keys and we convert it to a list, now we see Guido touring Bill. You can see it's not in any kind of order. If we ask for a list of password values, we get Super Programmer Genius blue screen. They're not in any kind of order either. We can ask for password and then call the method items, convert that to a list, and you can see that we have a list of tuples. Okay, again, they're not in any kind of order either. So all the lists that we just got don't happen in a definable order, but we could sort the list to put them in the order that we want. So then we can ask Bill in password true, Fred in password false. Okay, so the value for Bill is blue screen. So if we do a get and we provide the key Bill and the default value unknown, what do we get back? Well, because there actually is an entry for Bill and it has the value blue screen, we'll get back blue screen. But if we do the same thing for Fred, because there isn't an entry for Fred, we'll get the default value, in this case, unknown. And this turns out to be a very handy it turns out to be a very handy function this way. And if we wanted to clear password, we would call clear, and then you can see that it's empty. So we're going to write a word frequency program. This is a pretty typical example that we use when teaching how to use a dictionary. So let's write a program that analyzes text documents and counts how many times each word appears in the document. This kind of a document is sometimes used as a crude measure of style similarity between two documents. It's used by automatic indexing and archiving programs. Okay, so this is a natural language processing application, but a pretty crude one. Okay, if you were to take a course in NLP, probably your first version of a program like this would be already much more sophisticated than what we're going to do right now. So this is a multi-accumulator problem. So I always take exception when he calls these accumulators because they're counters. We're counting the number of occurrences of each word, okay? And I'll admit the counters are the trivial case of accumulators, but I would rather call it a multi-counter problem. We need a counter for each word that appears in the document. We can use a loop that iterates over each word in the document, incrementing the appropriate counter. The catch, we may need possibly hundreds or thousands of these counters. So it's not going to work to declare them as individual variables. So let's use a dictionary where strings representing the words are the keys, and the values are ints that count up how many times each word has appeared. To update the count for a particular word, W, we need something like this. So we're assigning a new value to counts W. Again, that's the word that we're on, and that's the key for this entry. And so we take the value that's in counts W already, and we add 1, and we store that back in counts W. Now, one problem with this code that we have so far is that the first time that we encounter a word, it's not going to be in counts. So if we did that, we would raise a key error exception. So we need a little bit more sophisticated processing, and here's the pseudocode for it. If W is already in counts, add 1 to the count for W, else set the count for W to 1. Okay. Now it turns out that a call to get is going to do a pretty good job. Okay. So this is the code. This version that we have on the top of the slide is kind of the rookie approach to this. And this, so I'm not even going to talk about it, but this more elegant approach is the way that people do it. So we call a get, and we provide 2 actual parameters. W is our key, and this 0 says it's a default value. So if we don't get a hit, then return a 0. And of course, when you add 1, that'll give you the 1 back. So this is an old programmer trick, an old Python programmer trick, and you'll find it gets used a lot. So we've got some other tasks that we have to do. In order to do this processing on the text, the first thing that we want to do is we want to make sure that words match each other even if they're in different cases. So in order to match Python with a capital P to Python with a small p, I guess it's possible to have a text where you want to pay attention to the capitalization because one is the language and the other one is the serpent. But we're not going to analyze anything that sophisticated, right? So our trick is we convert the text to lowercase so that we have no difference in capitalization. And then we eliminate the punctuation. And what we do is we find all the punctuation characters that we're expecting, and we replace each one with a space such that what we're left with is lowercase alphabetics and spaces. And once we have that, we can just do a plain old split, okay, and the split method of the string class by default works with things that are separated by spaces. And since we turned all of the punctuation into spaces, that's going to work just fine. So here's the code here. Let's see, we're going to open up the file. We're going to read all at one time. We're going to do a single read, and we're going to get one big string and put it in text. Then we're going to take that text and we're going to call lower and store reference back in text. So the text is now holding lower. And then we're going to go through it and we're going to say for a character in this, okay, this is a list of all the punctuation things we want to get rid of. We say text equals text replace the character with a space, and then we do we create a list called words by calling split on text. Remember, we don't have to specify actual parameter because the default is we split on spaces, and that's going to work just fine. And then we're going to loop through the words list. Okay. And here's what we're going to do. First of all, we're going to create an empty dictionary called counts, right? That's going to hold our accumulators or counters, right? And so then we say for W in words, counts W, index W gets assigned counts get. We use a W for the key, 0 for the default, plus 1. So we're just going to go all the way around and we're going to count all of these. So when we're done, we're going to have a dictionary with all the word values as keys, and then the values are going to be ints, which is the count of that word. Now, we want to print a list of words in alphabetical order with their associated counts, but we have a problem, and that's that dictionaries are inherently unordered. So even if we did a 4n, we could get the keys, okay, and we could use it to retrieve each of these things. But the problem is that it won't be in the order that we want it in. So this is what we're going to do. This is a standard approach to this. First of all, we call keys on our, and I may have said list when I meant dictionary a second ago. If I did, I apologize. So counts is the dictionary with all of our counts in it. So we call the method keys, and we get a sequence of keys. We convert that to a list, so we now have a list of keys, and we call that list unique words, okay? And then we sort that, okay? Well, that's a list of strings. It's going to sort in ascending alphabetical order, okay? I'm sorry. And then we can just use the keys as a thing the list of keys as a thing to iterate over. So it's now a sorted list of keys. So we can say for W in unique words, print W and the count W. Okay, so we're going to print out the counts. Pretty good. And we can do it in a particular order in this approach of retrieving the keys, sorting the keys, and then just retrieving the values and printing things in order this way. This is a standard approach to, unloading the dictionary and printing it in some kind of a sorted order. This will probably not be very useful for large documents with many words that appear only a few times, because you're going to have a lot of low frequency entries. A more interesting analysis is to print out the counts for the n most frequent words in the document. To do this, we'll need to create a list that is sorted by counts, most to fewest, and then select the first n items. Okay, we could do that. All right, so how could we do this? Well, we can start by getting a list of key value pairs. Okay, so if we call the method items on the dictionary count, we'll get a sequence of tuples. Okay, and each of the tuples will be key value. Okay, so we do that. We call items. We convert it to a list. It's called items. Okay, so it's a list of tuples like foo, bar, spam. These are 3 pretend words, and they each have a count. If we try to sort them with just by calling the sort method, they'll be ordered by components from left to right. Okay, so if we don't provide any key information, all right, then it's going to assume that the first field is the one that we want to sort on. That's going to be the primary sort order field. So it's going to put them in key order. We don't want them in key order, so that's not going to work for sorting. So what can we do? To sort the items by frequency, we need a function will take a pair, take a tuple, and return the frequency. Okay, so here we do. We just create a function, because we know how to pass a function to sort with the key. And we say that we're going to pass it a pair. Again, that's a name for a tuple. And then we return pair index 1. That's 0, 1. That's the one on the right. Okay. And then to sort the list by frequency, we can say items.sort key equals by freq. That's what we had called that. Okay. So there are times when you have a data structure that's kind of complex, more than one field, and you're not using instances of custom classes to hold the various components. Maybe you hold them in you have a list of tuples. Well, in fact, if you want to sort them, then you can just sort them like this. It's maybe not as good documentation, but it works just fine. So our program is coming along. We're getting there. What if we have multiple words with the same number of occurrences? We'd like them to print in alphabetical order. So if we have a tie, let's say we've got 3 words, one that begins with A, one that begins with C, B, one that begins with C, okay, and they all have 5 occurrences. We would like to show them as we'd like to show them each with a 5. We'd like them grouped together, okay, but we would like to see the A before the B before the C. So we want to list a list of pairs primarily sorted by frequency, but sorted alphabetically within each level. Okay. Looking at the documentation for sort, it says that this method performs a stable sort in place. What does that mean? Well, in place means that the method modifies the list that it is applied to rather than producing a new list. So it's going to change the order of the items that are in the list. Stable means equivalent items, equal keys, stay in the same relative position to each other as they were in the original order. Well, this gives us a great trick. So here's what we do. Um, so if all of the words are in alphabetical order before we sort them by frequency, words with the same frequency within that frequency group will be in alphabetical order. So we just need to sort the list twice. First by words, then by frequency. So this is how we do it. We have a call to sort on items. This is a list of tuples, right? By default, it sorts on the left or the first, but the zeroth field, which is the key, which is the word itself. So that's going to put them in alphabetical order. And then we sort them again, key by freq. And now we're going to say reverse equal true. And what reverse equal true means is descending order. So we're going to sort them in descending order of frequency. Okay, and if we have ties, then it's going to leave the ties in the same order that they came in, which is alphabetical order. It's a pretty sweet thing. So now we're ready to print a report of the n most frequent words. Here the loop index I is used to get the next pair from the list of items. The pair is unpacked into its word and count components. The word is then printed left justified in 15 spaces, followed by the count right justified in 5 spaces. So now we can say for I in range n, okay, we unpack each of those items one at a time into word and count, and then we print them. Here we're using again the way to format output that was used in our textbook that's kind of been superseded by F strings. And in my refactor version, I'll show you the F string version. But we're printing the word and then the count. Okay, unfortunately, this slide does not go any further, but I will. Okay, what does this look like, right? Let's see how this goes. So I've got more programs. So I've got one called Word Freak. Okay, so let me close all these. I've got too many things open. So Word Freak, this is the program as it came with the book. He never showed us the whole program on one slide because it's really too big for one slide. Okay, so he walked us through, and it's got the same usual warts on it that we've had in a lot of the other programs. Not enough blank lines. Oh, it's, well, a lot of things. So I've refactored this into Word Freak Refactored. Okay. And let me show you what I've done here, okay? First of all, I've given it a proper doc string. Okay. Program analyzes word frequency in a file. User specifies the name of the input file. User chooses the number of most frequent words to report. Program prints reported most frequent words. Okay. And we have a main, okay, in which we print some kind of introductory message. And whereas in the code that we saw from the book, this is all coded into main. This is just one long kind of run on main. And is that too long for main? Yeah, as long as it fits on a page, I think that's probably okay. But the problem, the problem that you get when you don't take uh, bits of related code and factor them out into methods, then you don't have method names. And so you have to insert these um, comments to tell the reader what's going on. So what I've done in the refactored version is I've taken each of these groups of code and I've extracted them into methods, okay, and they each have a descriptive name. So there's one where we get the text. There's another one where we prepare the text. There's another one where we count the words. And then there's the last one where we print the report. Okay. And then we have the function by frequency, which is used in the sort, the second sort that's in the report. So when you do that, then the main reads, as I like to say, like a children's book. Okay. So we call get text, and we save this big string object in a variable called a text. The one where we process it and shift it to lowercase and get rid of the punctuation is called prepare text. Okay. Now, here's what I do. I pass in text, and then I save it under a whole new name. There's another context. It's prepared text. Okay. It's not the same context. Use the new variable name. And then we want to use the split method of this string object to split the one big string into a list of words. And then we have a function that counts the words and puts the counts into a dictionary, which we get back as counts. Okay. And then we ask the user how many words they would like to show. He used the variable n. I typically would use a better variable name, but he did. And then we call print report, and we pass it the counts dictionary and n, and then we print the report. Okay. And when we print the report, we unload it into a list of items. Okay, we sort the items. That's going to put them into alphabetical order by key. Then we sort them again. The key by frequency, reverse equal true. So we're going to have these things sorted by the count, okay, but within equal counts, they're going to be in alphabetical order. Okay, and then we just say for I in range n, we unpack them and we print them, and you can see I've used the more contemporary F string instead of the formatting that was used in the book and on the slides. Okay, so how do these run? Well, first of all, he didn't really give us any text, so I decided to find some text. I went to the Gutenberg project and I downloaded the Meno by Plato, which is one of Plato's dialogues, and it's a classic old philosophy text. Okay, and so we have that here, and when we go to run it, okay, if we run WordFreak refactored, it's going to ask us file to analyze, and it's Meno by Plato dot text, and how many words would we like, and let's say we'd like 75. And if you look at what we have, this looks like it's about 75 words. There's a whole bunch of words up front that have very high counts that we probably are not interested in. And people who do real natural language processing applications have a further concept that they introduce. They have this thing called a stop word list. So there are certain words that they just ignore. And things like the, of, and, to, is, in, a, that, those are all things that would probably come to a stop word list. So the other things would be higher. Okay. The first really important word is Socrates. He's one of the characters in the dialogue. Meno is the other speaker in the dialogue. He's there a lot. And we've got a bunch of potential stop words in between. One of the interesting is, I think the very last word is Plato. Okay. So again, this is very crude textual analysis. If you were to take a natural language processing course, I would think that your first example would be more sophisticated than the one that we did here. But this is a great use case for dictionaries. And you'll note here, one of the things that we wanted, let's see, there are 3 75s, okay, and they are in alphabetical order, A, H, S. Pretty cool, huh? So that is the end of the lecture for this chapter, and I'm just going to say bye until next time. Bye-bye.